Remember this important formula from 2.4. If I want to find the slope of a curve at a particular x value, I'm going to use the difference quotient. I'm going to pretend I have 2 points on the curve, even though I only care about 1 point. Pretend I have 2 points and let them get closer and closer and closer together till essentially the distance between them is 0. So we have an example like this one. I have a function, f of x is negative 16x squared. I wanted to find the slope of that curve at exactly the place where x equals 5. So in this case, I'm going to use that difference quotient, that formula I had on the last slide. I'm going to let a equal 5 because that's the x value that I care about. So I'm going to take my 5 plus h and FOIL it out to square it. Once I cancel out my 400s, now I can factor out an h and it'll finally cancel with the h in the denominator. And you can see up here at the top of the right-hand column, now that I cancel out the h, I can plug in 0 for h and I have no problem. I end up with a single number value, which is negative 160. So the slope of that curve, when x equaled 5, is negative 160. But remember the example we did right after. I want to find the slope of a function, 1 over x. I didn't give you an x value. I said just at some x, then I'm just going to give it a letter. I'm not going to actually tell you the number. I'm just going to find the slope of this curve at a. So we went through that whole same process. We're going to take the limit as h approaches 0 of f of a plus h minus f of a all over h. So this is us picking 2 points, a comma f of a, and some point a little tiny bit further away. I'm going to let the 2 points get closer and closer. So we did that same math, but we didn't have any problem not knowing a. We just ended up with an a in our answer. So I can get a common denominator for my numerator. Once I have a common denominator for the numerator, I can change to multiplication by the reciprocal of h. So this is the times 1 over h I have up here in the top corner. And again, I'm able to cancel out an h in the numerator and denominator. And I can plug in h for 0 for h now without a 0 in the denominator problem. And I was still able to do the problem. I got that answer there, negative 1 over a squared. And what we said was this was a little expression. Now that I had done the math sort of abstractly without having picked an actual value for a, now I can decide. I think in the problem, yeah, I asked you to, now that you had that expression, negative 1 over a squared, what would the slope be at x equals 2? Well, that just means I'm finally deciding what value to give a. I could let a equal 2, and I could figure out that the slope would be negative 1/4. This is a big topic in calculus. In fact, it's going to take up the whole rest of our first half of calculus. Finding a formula that you can use to give you the slope of a curve at any point on the curve. So the only difference between what we just did and the whole topic of chapters 3 and 4 is we're going to formalize the notation a little bit. And notice that here, let's see, I used an a in my expression. I'm just going to rewrite my work so that I could use, there we go, so that I could use x in my expression. So I can think of my function at the end as a function of x. So I could plug in an x value and get the slope of the original curve at a particular x value. So watch this. So this is the notation we're going to use to formalize that process that we just practiced. Finding a function, naming a function that can give you, at any x value, the slope of the original function. So we say, I'm going to read this, this is f prime of x. So the derivative is a function that gives the slope of a function at any x value. We would say f prime of x is the limit as f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. We call this function, the function that we're looking for, we call it the derivative, or more specifically the derivative of f with respect to x. And this is the definition that goes in that top box as the very first thing to fill in on your notes paper. So there's several notations that you will see over the course of the year for the derivative of a function. probably the most common is this first one here, f prime of x. So an expression for the derivative of f. If I give you a function f of x and ask you to find its derivative, you will label your answer with f prime of x. You could also read that as the derivative of f with respect to x, with respect to whatever letter is inside those parentheses. A slightly less common way that you might see this notation, if I give you a function in f of x notation, you might refer to the derivative as df dx. That's this one. It's less common. df dx, or the derivative of f with respect to x. This is not a fraction. It's just one big symbol that means the derivative of f. If instead of giving you the original function in f notation, I gave you the original function in y equals notation, these next two are pretty equally common. So you would say, if I wanted you to take the derivative of y, you would refer to the derivative as dy dx, dy dx. Again, it's not a fraction. It looks like a fraction, it's not a fraction. It's one big symbol that means the derivative of y. Another way you could write that same expression is with the notation y prime. It means the same thing, the derivative of y. And then one more notation you might see, again, if I gave you a function in f of x notation, and I asked you to take the derivative, you might use this expression, you might use this expression to say, I'm taking the derivative of f of x. So this one's a little bit different. d dx is an operator. It's an operation. It says, I'm going to do something to the thing that comes right after. So this means I'm going to take the derivative of, in this case, f of x. So the notation here, the phrasing, the words here are is d dx of f of x, or the derivative with respect to x of f of x.